All right, thanks everyone. Thanks so much to the organizers for organizing this workshop. It's been really wonderful, and I'm excited to be able to share some thoughts here today. So I'm going to talk today, I'm going to give kind of a broad talk about inference and privacy and some of the ways that I think about inference and privacy and some of the work that we've done in this area. So the starting point, I think, as we're sort of all aware, is that there's now been a tremendous amount of research on differentially private algorithm design, and to approximate many different interesting statistics of a sensitive data set. And one of the really interesting implications of this is that algorithms that didn't used to be randomized are now randomized. All right, so this leaves us with a problem of trying to do inference over what the true statistics were given the privacy-preserving output. So this is really fascinating if you come from a probabilistic inference standpoint, which is sort of my background. It's a wonderful source of probabilistic inference problems where you sort of know exactly what the noise mechanism is. You want to uncover some true hidden quantities. So this picture this captures the sort of big picture that I want to think about today. So we know we have a sensitive data set here, which consists of, let's say, n records. And we have a randomized algorithm here that releases some privacy-preserving output beyond this privacy barrier, which will be represented by this vertical line here. And we may or may not also be in the situation where we have some statistical model with a population parameter that governs how we think the data was actually generated. So then the inference problems are, given this privacy-preserving output, which, this has been designed to approximate something we care about. It might be some simple statistic like the mean, or it might be something more complicated like the parameters of a deep net, or in the context of this workshop, maybe noisy measurements, which were released by the Census agency. Well, what problem do we want to solve? The inference problem is, given this privacy-preserving output, what can I say quantitatively? What do I actually know about either the data set itself or the parameters of this statistical model by which we assume the data was generated? Okay, and so the research questions in this area is, like, how can we use the principles of inference, either probabilistic inference or statistical inference, to both design new algorithms and improve existing ones for differential privacy? And there's many potential benefits. I think we're aware of this. Many people in the room are sort of already thinking deeply about these problems. And I sort of like to divide this into two different settings. The first is the statistics setting, where we indeed do have a model by which we think the data was generated, and we have a population parameter, let's say, and we want to do inference over the population parameter. The second, which is also quite relevant, is the database setting, where we maybe don't have a model, and we actually want to perform inference over what the records were themselves, the data set itself. And so I'll talk just a little bit about some work in both areas. So to start, in the statistics setting, there's been a lot of work on private estimation. And I think that many of us recognize that sort of an important frontier is to develop practical uncertainty quantification methods to go along with private estimation. And really, I think an ideal here should be something like these really general purpose tools that we have that we can apply in the non-private setting. So if you talk to somebody who's working on an applied statistics problem in a non-private setting, like, they almost never don't know how to construct a confidence interval. Like, there are these tools like estimate the Fisher information or perform a bootstrap that allow them to sort of, if they can do estimation, they can easily construct confidence intervals. And I think that should be like a goal that we think about as the privacy community, to develop sort of these general purpose methods that can work for privacy preserving estimation as well. Okay, so just to make the setting a little bit concrete, let's look at one particular model. It's a simple model. And okay, so this would be an example of a statistical model. In this case, we'll assume that our x variables, we have n of them, are each just coin flips. They're Bernoulli random variables with some parameter theta. And what we want to do in this case is inference about theta. What was the probability of success for this coin flip? We're going to release some privacy-preserving statistic. If we want to estimate theta, a sensible thing to do is just take the average of all these 0, 1 variables and then perturb it by adding a little bit of noise. And then we may or may not be in a Bayesian setting, and if we are in a Bayesian setting, we'll also come with some prior beliefs in the form of some prior distribution over theta. So concretely, what are the problems we want to solve? Well, in the Bayesian setting, we would want to quantify uncertainty by computing the posterior distribution. So this means computing the distribution of the parameter given the privacy-preserving output. And one thing that I want to note is that it's explicitly not a goal to privately approximate the posterior distribution that we would have had if we could have observed the true data. This is something that is sometimes done, and it's also sometimes correct asymptotically, but in general, it doesn't quantify your true posterior beliefs of the parameter given the privacy-preserving output. And then in a frequentist setting, of course, we want to estimate the parameter, and we want to construct, let's say, a confidence interval for it. And I think sort of at a high level, one of the key ideas that I would sort of like to put forth is the idea that resampling methods can be very effective at cleanly reasoning about both sources of randomness in this picture. So we have the sampling error, or the sampling randomness by which we imagine our data to have been generated. And we also have the privacy noise, where we know there was a randomized algorithm that was run to produce this privacy-preserving output given our data. And the general idea of a resampling method is that, well, we observe this privacy-preserving output. So given that privacy-preserving output y, we can resample the data and the parameters from appropriate distributions to reason about the distribution we care about. And that was kind of deliberately vague because the exact way that you do it will differ depending on whether you're in a Bayesian setting or not. In a Bayesian setting, sort of a conceptually simple way to do this resampling is via a Gibbs sampler. What does a Gibbs sampler do? It initializes both the parameter and the data arbitrarily, and then it repeatedly updates each one of them by sampling it from its conditional distribution, given the fixed values of the other variables. Okay, and so why is this good? Well, why does this cleanly reason about sort of both sources of error? Well, if you think about, for example, resampling the data conditioned on the parameter and the output, this is sort of directly thinking about both the conditional distribution of the data given the parameter, that's the sampling noise, and the conditional distribution of the output given the data, that's the privacy noise. So, of course, the challenge is actually figuring out how to solve these inference problems, which can be challenging depending on your particular model and release mechanism. And in a pair of papers in 2018 and 2019 with my former student, Garrett Bernstein, we showed how to do this for some particular classes of models, in particular exponential family models and Bayesian linear regression models, where the release mechanism was noisy sufficient statistics. And one of the insights of that work in that particular case is that we were able to make it more efficient by actually not reasoning about all of the individual records as latent variables, but actually aggregating to the level of sufficient statistics, which was beneficial. In the frequentist setting, the most common resampling type methods are bootstrap methods. And so now I want to change the picture just a little bit and imagine that my privacy-preserving output now is not something arbitrary, but it's actually an estimator. So it's actually an estimate of my parameter theta. So in a paper led by my student Cecilia Ferrando this year in AI Stats, we advocated for the parametric bootstrap as a very simple but extremely effective method for constructing confidence intervals for parametric estimation problems with differential privacy. And what I think is really nice about this is it works really for a very general class of private estimators. So it sort of frees you up to design your estimator the way that you want, and then it's a pretty easy way to get confidence intervals given those estimators. So it's nice in the settings where it applies. And the idea of the parametric bootstrap is to actually simulate new data sets from the model where you use the estimated parameters in order to draw new data sets. There's no privacy cost for doing that because you're just generating from a model. And then to rerun your randomized estimator. And again, you're simulating both sources of randomness, so this cleanly reasons about both sampling noise and privacy noise. And we showed in our paper that you can get consistent confidence intervals this way for several different models. and that these confidence intervals perform well even at very modest sample sizes. Okay, so with that, I want to switch gears and talk a little bit about the other setting I talked about at the beginning, which is what I call the database setting, where the goal is to perform inference over the data set itself. And here I'm going to talk about a work called private PGM. PGM stands for Probabilistic Graphical Models, and this was joint work with Jerome Miklau and Ryan McKenna at UMass. And what private PGM is a general purpose inference method for tabular data given noisy marginals. Its primary uses so far have been in query answering and synthetic data generating mechanisms. Okay. In the problem setting, or the sort of big picture here, the idea is that we want to estimate a data distribution here given some observed noisy marginals in order to reconstruct an approximate data distribution for the purpose of solving downstream tasks. And there's sort of two changes in this picture. One is that I'm using a data distribution instead of a data set. I'll talk about that in the next slide. And the second change is that I'm assuming that my privacy-preserving output are explicitly noisy marginals of this distribution. And they can be any marginals. For the purposes of illustration, I have a little graph here with edges representing two-way marginals. So the presence of an edge in this graph means I get to observe the noisy marginal on those two variables. Okay, so what is the data distribution? This is actually something that I think is very familiar to this audience. This is a useful alternate representation of a discrete data set, and it's nothing more than the histogram that Michael talked about, I think, in the first talk yesterday. So to remind everyone, so this takes all possible records in the data domain, and it looks at the actual data set, and it counts the number of times or the frequency with which that record occurs in the original data set. I'm going to think of this as being normalized to sum to 1, so it's a distribution, as opposed to being summing to the population size. Also, just as an alert, this is something that differs from some of the work in this area. We will consider continuous relaxations when we're doing our inference problems. Okay, so one of the things about this data distribution is that there's a very, very large number of possible records if you have many attributes. So the full histogram or the full data distribution has exponential size in the number of attributes, which is a significant limitation if you're trying to reason about it in practice for high-dimensional data sets. And so the goal of this work is to try and find a computationally tractable representation of the data distribution over which we can perform inference. Okay. So why do we want to do this in the first place? Well, the main reason we want to perform inference is that there's a lot of power in having a reconstructed distribution. With a reconstructed distribution, you can answer new queries. You can answer queries about marginals maybe that were not directly measured by your noisy release mechanism. While answering queries, you can often reduce error and ensure consistency by using inference over a consistent underlying model. A second reason is that this subproblem appears very often in query answering and synthetic data generating mechanisms. In fact, it often occurs at every iteration of query answering or synthetic data generating mechanism. Those, for example, these are mechanisms that have a large workload of queries. They measure some of them, and then after measuring some of them, they want to be able to answer all of them to see what their error looks like. And this is exactly the technique that you would use in order to answer all of the queries given only noisy measurements of some of them. And then, of course, I think the reason that we're all assembled is that there's a chance that the census will release noisy measurement files. Thank you. This is potentially applicable in that setting as well, where we would have actually measurements of noisy marginals. Okay, so how do we solve this problem? Well, if the data distribution fit in memory, there would be a fairly direct way to do this by solving an optimization problem, for example, a least squares optimization problem. The general principle is to find the data distribution that is most likely to have produced the marginals that you actually observed. So this would involve, for example, comparing the noisy marginals to the marginals you would have gotten with distribution P, and that's going to involve some sort of marginalization operator to compute the marginals of distribution P. Okay, so that would be nice, but unfortunately, this is an exponentially large object and it doesn't fit in memory. So the sort of key observation of private PGM can be summarized by this fact. And the fact is that there actually is an optimum of this problem where the distribution is actually a graphical model. So a graphical model is a distribution that has a compact representation as a product of factors. And factors over smaller sets of variables. And in particular, the form of this graphical model is factors will exactly match the noisy marginals, the things that were actually measured by the release mechanism. So the dependence graph of this graphical model is exactly the graph I showed before when I was sort of introducing the noisy marginals. This is nice because it's sort of this distribution can be represented with space complexity and the computational complexity of both sort of finding this graphical model and using it to answer downstream queries is of the same order as probabilistic inference in a graphical model. And this is a well-studied problem, and we sort of know how to do this, and we know what its limitations are. And in particular, there's good news and bad news. The good news is that for nice enough graph structures, this is much, much faster and uses much less space than constructing the full data distribution. It can be exponentially faster. But the bad news is with complex enough graph structures, we still run into tractability problems. Okay, so I'll sort of move towards wrapping up. Okay, so this has been, we think, an impactful project. So we showed in our original paper on this, which appeared in 2019, that private PGM can effectively both improve the utility and or the scalability of several state-of-the-art query answering mechanisms. Private PGM was a key component of several top entries in the recent NIST competitions for generating private synthetic data. This was both by UMass teams and some other teams in the second competition. Ryan McKenna, who is really the engine behind a lot of this work, has produced easy-to-use open-source software where you can use private PGM to quickly get started generating synthetic data, for example. And there's been follow-on research both by ourselves and some other groups to try to explore this sort of interesting computational tractability trade-off where this can improve the situation a lot of times, but also there are limits. And so there's some very interesting questions in how to, for example, design mechanisms that respect these computational limits. Okay, so with that, let me conclude and just thank my key collaborators on this work. And if there's time, I'd be happy to take some questions.
Thank you, Dan. Any questions? Oh, Robin?
Thank you, Dan. This is Robin speaking. This is fantastic work, and I really loved it. As I said to you earlier, before yesterday, that your work, especially on the statistical, I guess the statistics setting, was something that was an inspiration for my work and my collaborators. I have not thought carefully about the frequentist setting. I'm by training, I guess it's not something that I think about too much. But so in the case and in the parametric bootstrap situation that you described, I guess my question is, so you have this. Basically, there's the mechanism goes like you need to sample the P of X given the hat of theta, which was the estimator that was differentially private. And I'm curious, how do you go about constructing that?
Sorry, this one here?
Yes.
Oh, so this is, sorry, yeah, maybe the notation is not perfect here. So this is a frequentist setting, so we have a probability model. So I'm assuming we have a fully parametric probability model for my data x1 through n. And now I'm just taking this theta hat and plugging it into that fully parametric probability model. So this is actually not a conditional distribution I think the sloppiness here is there's not a conditional distribution on the theta hat random variable. this is just using theta hat as a plugin.
Sure. So you have essentially it's px given theta where theta is equal to theta hat. So you're sampling from that.
Yeah. So I have a generative model, and I just sample from my generative model.
And so my question, I guess, is like, where does the differential privacy mechanism come into play?
Oh, so this is pure post-processing. So theta hat is a private estimator, and I receive theta hat, the private estimator. And then the parametric bootstrap is 100% post-processing. I draw new data sets from the parametric distribution, and I rerun the randomized estimator, but there's no more privacy implications because I'm just rerunning it on simulated data.
I'm not worried about the privacy implication,
Yep.
but I'm saying, for example, we can imagine there are better and worse sort of there are different ways to construct theta hat, all
Yeah.
of them being differential private.
Yeah.
And is there something in the process that will take that generated process into account?
So we're always rerunning the same. So I think you may be asking about, like, there can be good and bad estimators.
Yes.
Yeah. And so this will correctly quantify the uncertainty of both good and bad estimators. I mean, there's some errors, of course, but like, I think one of the benefits is you can apply it to both good and bad estimators. If you have a bad estimator, you will have more variability when you rerun the randomized estimator on the simulated data sets. It'll also take longer to converge to the correct thing asymptotically because when you're resampling these data sets, they're not as close to the correct distribution.
Right, and I think, as you said maybe 2 slides ago, that there is a way for you to look at the result from this parametric bootstrap and be able to sort of tease apart the privacy error part of the error and the sampling part of the error.
Well, actually, that's interesting. We haven't looked explicitly at teasing them apart. Our goal was to like actually have a method that correctly accounted for both of them without trying to look separately at them.
Great, thank you.
Yeah.
I too really loved the talk. May I
Thank
ask
you.
you please to go back to your slide on private PGM?
Sure. Is it this one?
This one.
Yeah.
So you say that there's an optimum that p-hat that is a graphical model. And then you talked about tractability issues when the graphical model is complex. So do you assume that you know something about the graphical model structure before you start your search? Like, what's the order of events here? And does the complexity kick in and surprise you, or is there a chance of misspecification and looking in the wrong places?
Yeah, these are great questions. And actually, the order is you know ahead of time what the structure of the graphical model is, and it's determined by the set of marginal measurements that you are given. Okay. And the structure of the graphical model is exactly the graph where two variables are connected if they co-occur in some measured marginal.
Okay.
And that determines the computational complexity. And so you sort of know what it is in advance. That's nice if you're designing mechanisms, actually, because you can choose not to measure things that you know would like make inference become intractable. Actually, and to be very concrete, it depends exactly on the tree width of this graph.
On the what? Sorry?
The tree width of the graph.
Mm-hmm.
So it's exponential in the tree width of the graph. So that's great it's nice when you're designing the mechanism. On the other hand, if you haven't designed the mechanism, which is the case with noisy measurements files, you may have to grapple with intractability. So that's, well, but it's both good and bad. I mean, in some ways it's fundamental, this intractability. But one of the nice things, I think, is that there may be methods from the approximate inference literature for graphical models that could sort of help you in that case.
Great. Thanks so much.
Hi, Dan. Thanks a lot. Interesting work. I want to go back to the parametric bootstrap. So I'm just curious, to the extent that you're familiar, the parametric bootstrap.
Yeah.
Okay, so
Sorry.
fine.
I just thought
It's
about
okay. I mean, I can still talk about it. This is a very common procedure in statistical disclosure limitation, where we fit a model, take a parameter estimate, and then we draw samples. Basically, that's how we create synthetic data. There has been also work back in, oh my God, let's say 10 years ago. I have to go like a look. where they've done something in a very specific setting with binomial distributions and things like that, doing exactly what you're doing here. So I'm just curious, what are the, I guess, are you providing certain generalization here? What are the additional methodological and theoretical results beyond what was in some of these other previous works? And again, SDC had no DP, it was just a very similar setup here. You take the theta hat and you simulate in the same way as you are. But there were some papers also doing with DP. I'm assuming you're providing some extra generalization here, or?
So I'm not sure. So the first setting you described, I'm not exactly familiar with the SDP stuff you described. It sounds a little bit different to me in the sense that it sounds like the parametric bootstrap is being used as the method of privacy preserving, or of like privatizing or sanitizing the data, where our setting is slightly different in that a different method was used for the privatization, and now we're using the parametric bootstrap to simulate it for the purposes of
yes or no. It's been done before in SDC as well, where you have some kind of, let's say, sanitized estimator through some other SDC method, and you can still sample from that space. We can talk about it then.
Yeah,
okay,
yeah,
so maybe you are not
talk
familiar with
offline.
that, so it's fine. And I'm just curious to understand the similarities and differences.
Yeah, it would be great to talk about it offline. I would summarize that really the main thing we're trying to do is advocate for this as a simple method,
Yep.
which we think applies to many private estimation problems in order
Yep.
to provide confidence intervals. Yeah, and maybe we could talk more offline
Yeah,
about the
okay,
connections
thanks.
to some other things.